Alright, so in this section, I'm going to have to pull a lot of visuals from the book. So these are things I can't draw from hand or by hand. Definitely beyond my skill level. So you're mostly just going to get some narrated pictures. I'm afraid there won't be my usual wonderful handwriting here. But we're going to talk about the stacking of these solids. And so the first thing I want to introduce is the unit cell. And so the unit cell is the smallest piece of the repeating structure. And so think of it like the Lego piece that you stack together with other Lego pieces, something like that. Now the key thing is that the faces all need to be the same so that they can stack together. So they need to meet at the face. You can't have like an atom that cuts off half in one cell and doesn't show up in the other. So that means that all the faces need to be identical. And so that's kind of how the unit cell lines up. In this example, there aren't really atoms. This is mostly just showing how the pieces connect together. So on the right, we have multiple unit cells forming our solid. All right, so unit cell, again, it's like the smallest piece. There's hundreds, thousands, millions of unit cells in a solid crystal, but it's the same piece repeating over and over again. And so what we get is the situation on the left here. We just have, I said it before, I'll say it again. We're just stacking spheres together. There's a few different ways we can do it, and this would be one that gives us what we call a simple cubic lattice cell, or simple cubic structure. So all the spheres just touch. They're not shifted together. So there is more open space here. They're not sliding. You could, if you slid the top row to the left, they could actually slide down a little bit, and you get denser packing. So there aren't a lot of things that are simple cubic lattice cell because it's not an efficient use of space. There's a lot of open space. But if we chop this structure up, these four spheres that are stacked together, you get the unit cell on the right. And so in this structure, we have just the pieces that line up. Now, if we stack this together, we start getting whole spheres. So everything lines up. If I stack one face against the other, all the pieces go together. So this is a valid unit cell. And from here, it goes up in complexity, but also in packing efficiency. So next, sorry, I forgot. So the size, the dimensions are going to vary depending on what type of cell it is. So this is the first of many. And it's 2 times the radius of your spheres, of your atoms. Because there's one radius here on the bottom and one on the other half of the bottom. And so you get 2r. So this one's pretty straightforward for calculating the dimensions of. And the easiest one by far. It gets more complicated after that. So next we have the body-centered cubic structure. And so this space in the middle is occupied by another atom. And so now there's these 4 silver atoms on top, these 4 silver atoms on the bottom that are overlapping in the corners. And in the dead middle of our unit cell is an entire atom. And it could be the same as the rest. So here it's just changed color so it's easier to see. So this could be a metal solid where they're all the same type of atom. This could be an ionic solid. And then in which case you would have cations and anions here. So it just depends. But that's another situation. So body-centered means there's something in the center. There's a body in the center. There's another atom. Versus, again, simple cubic, there's nothing in the middle. So this is going to have a higher packing efficiency. There's going to be less unused volume in this setup. And then after this is face-centered. And so what this has, or in the center of every face, there is half an atom. It's been cut in half. Whereas the other half, well, it's in the other unit cell that you push against this one. Okay? Just like there's only 1/8 of an atom in the corners here, you got to put together multiple unit cells to get a full atom. You got to put together 8 of them. All right? So this is another stacking structure. Again, higher efficiency than the simple cubic cell. And in this case, you notice I skipped over the dimensions of the last cell because it's complicated. This one's not too bad. So it's 2r on the diagonal. So a squared plus b squared equals c squared. And so you can solve for the sides if you know the diagonal. And again, the unit cell, it's going to depend on the size of the atoms. So they're not all the same size. So some metal atoms are bigger than others. And then we'll get into talking about ions in a little bit as well. They're more complicated. And molecules, we're not even going to touch those because they're not even sphere shaped. So it gets messy. All right, so I talked about simple, face-centered, and body-centered with pictures. And there's a few different varieties just depending on, if you're dealing with the same compound, maybe you've got two different atom types or three, or, maybe you don't have 90-degree angles in your unit cell. That's a possibility. So it's not a cube anymore. These get more complicated. And so things like these hexagonal and rhombohedral, well, that has to do with what happens when they start kind of slipping closer together. So they're not touching, top and bottom. Now they're kind of sideways to each other. And so that gives these more complicated unit cells, but they do have a higher packing efficiency. So it depends on how attracted to each other these atoms are. It also depends on, the size, how well they fit together. There's a lot of variables that go into it. So there's no need in this class to be predicting what type of unit cell something is going to be. It's just what type are you looking at? Okay, let me be clear about that. So you see this and you go, oh, that's body-centered cubic. You see this, you go, oh, that's simple cubic, and then, oh, that's face-centered cubic. Okay, that's all I'm looking for. And there are, a few other options, but we're not going to worry about that too much. Now, when you do get into ionic compounds, there's an added complexity. So metals are nice. Okay, metals are like this. They're all the same size. We're stacking spheres. They're all the same size. They might have different levels of attraction. They might fit together differently. You might get body-centered cubic. You might get simple cubic. Face-centered cubic, just depends on the metal. But all these atoms are the same radius. There's an issue with ionic compounds. Cations and anions are not going to be the same size. So you are stacking together two different size particles, and they're not all going to have the same attraction to each other. So the pluses and the minuses are going to attract, and that's it. Pluses and pluses are going to repel, minuses and minuses are going to repel. So you have all these different factors for size. You have the attractive forces between the anion and the cation, and you have the repulsive forces between cations and anions and anions. And so you have all these different situations, and depending on the relative sizes of the ions, you can get some really weird packing. You can fill these tetrahedral holes, or if they're similar enough in size, you get these cubic holes filled, so they just fit together differently. Okay, so you're mostly dealing with tetrahedral and octahedral holes for ionic compounds. But the main thing is just if you're given a unit cell, can you find the formula? And so the first thing is cations are going to be small, because remember their electron shell shrinks, and anions are going to be large because their electron shell grows. They're picking up extra electrons. And so when we look at the cesium chloride here, notice how these atoms on the corners are larger than this one in the middle. Well, that means that's cesium in the middle. That's the cation. And on the outside are the anions because they're larger. That's how I can tell. The next thing is I go, oh, this is a body-centered cubic cell. Okay. And then if I didn't know the formula, how could I figure it out? You just count up the atoms inside the unit cell. So on the corners, that's 1/8 of an atom. Because remember, it's only this piece right here that's in the unit cell. So even though they're showing the whole sphere, only 1/8 of it is in the unit cell. So I go 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, 8/8. So there's one chloride, and then there's a whole cesium in the middle, so it's 1-to-1. So it's CS1, Cl1. If I look at something a little bit more complicated, like the zinc sulfide, I've got a whole lot of stuff to count here. So this is a much more complicated unit cell. It's not body center, it is face center with some holes filled. That's what we're looking at here. So the corners 1, 2, 3, 4, 5, 6, 7, 8. All right. So that's 1 zinc, and then I've got 1. Now these faces are halves, okay? Because where is it? There's only a half of it inside the cell. The other half is outside. So I've got 1, 2, 3, 4, 5, 6. So that's 3. So I have 4 yellow zincs, and then these are in holes. So these are actually entirely inside the unit cell, and I have 1, 2, 3, 4. So it's 4 zincs. I'm sorry, the yellows are sulfides. So 4 sulfides and 1, 2, 3, 4. The smaller spheres are the zincs. So 4 zincs. So that's 1 zinc for every sulfide. So it's just ZnS. So we just confirmed the formula. Now, it looks like we have a similar situation here. Now you'll notice that the small sphere, that's going to be, actually it flips on this one. Turns out calcium's larger than fluoride. So it is actually the fluorides out here. But in general, it's because they're so far apart on the periodic table that this happens. So it can get a little bit tricky. But anyway, we can count this up and we get a similar result. We find that there are 2 fluorides for every calcium. All right. Now the one situation that was not shown here was if there's something on the corner. All right. If there's something here, it's like, it's half of a face, right? So if it's on the edge, it's going to be 1/4 of an atom. So these are 1/8, these are 1/2. Inside is 1 whole, and on these corners is 1/4. And we're not going to get into, so metals, all the atoms will be the same size. So you're stacking all these balls that are the exact same size. Ionic gets complicated because the difference in size can cause different stacking. And it's not always a 1-to-1 ratio. You can have 1-to-2, 1-to-3, 2-to-3, whatever it is for the ionic compound. And molecular, we're not getting into that. Because then we're not even stacking spheres. It's a whole other ballgame. Okay? And even stacking spheres is complicated enough. I mean, that's a math problem that has not been entirely, perfectly, completely solved. There's no general solution to the stacking problem to this day. So to complicate it by having things shaped like a boomerang or whatever, forget it. Now the last thing I'm going to show you, and I totally forgot to pull a picture from your book, so pardon me here, is that we can get defects. So I save this till the end. Alright, so depending on the size of the atom, we can get a defect that either does or does not affect the structure. Alright, so things are stacked nicely. You can get a substitution where a different element atom just pops in and it's about the same size. The lattice structure stays the same. You can have a vacancy. You're just missing something. Okay, again, it doesn't throw off the structure. There's just a weird gap in it. You can get an interstitial impurity, and that's where an atom is small and it's able to fit in the gap. So, if you have something that's like a simple cubic structure, maybe there's an impurity that can actually fit in the middle of one of these unit cells. All right. And then there is a substitution where the atom is larger than the normal atom in this crystal structure. And that's going to mess things up. You're going to see a massive defect from that because it's going to occupy extra space. It's going to mess with the lattice structure in a big way. And so you can get these different kinds of defects. Now, when you make a semiconductor, you're actually intentionally forcing these kind of defects into a solid crystalline or crystalline solid piece of silicone. So you have your silicone wafer and you dope it with different metals. That's how you produce a semiconductor. You're actually intentionally introducing impurities to the silicon. So, and then a really cool thing is one of the potential sources of quantum computing is actually to substitute into a diamond 1 nitrogen atom. And so it's about the same size as carbon, and so you get something like this, but you don't have 4 bonds like you would with carbon. You have a lone pair. And you can do quantum computing using the electrons of that lone pair in the nitrogen. So you kind of create an electron, a bonding void with electrons that you can manipulate the quantum numbers of. So, these are incredibly important to material sciences and things like quantum computing. But, for this section, just to understand what a unit cell is, and if you want to calculate the density, then you have to use the dimensions to calculate the volume, and then you'll be given like the mass of an atom. So you have to figure out how many atoms are in a unit cell, divide that by the volume, and then yada yada yada. I'm not too big on that. We're not going to worry about it too much, but just a heads up that you could do that. But the dimensions, yeah, for a simple cubic or face-centered, I expect you to be able to calculate the dimensions of that, do a little bit of geometry. That's fair game. And then for the most part, start with simple face-centered, body-centered, and then just understand that you can get more complicated cells with the result of more efficient packing. End up happy there. So there's a lot here. You can get these hexagonal packed systems, and they're going to have the highest packing efficiency of the group. But man, do they give you a complicated unit cell, am I right? So, I'm not going to expect you to do much with that. And then, these different types of holes, just understand that there are, different results that can happen. So you can fill in the middle of the unit cell if things are the right size. You can pop into the lattice structure as well with things that are a little bit smaller. And if things are about the same size, then they pop, into like body centered or something like that. So that's what you see over here. All right, so I believe that's everything. So, coordination number. Almost forgot. So coordination number is just, you pick like this purple guy here. It's got 1, 2, 3, 4, 5. It's got a coordination number of 5 because there's no atom over here. So it's just, how many axes come off of it that connect to other atoms. Versus this orange one here, it's got 1, 2, is it 5 again? All right. Well, anyway, that's all you do. You just follow along. So 1. I'm trying to find one with a different coordination number, and I'm not seeing it. All right. So yeah, I think that's it for now. So coordination number, if it's like base center cubic, or I'm sorry, basic cubic, base center. That's not a thing. Last video of the night. Then it's going to be 6 because you have 1 off of every axis. So that's what it ends up being. And it just goes down from there. Okay, so yeah, and then being able to find the formula for an ionic compound from the unit cell. That's probably the trickiest thing I expect. So that'll do it for this chapter. Yeah, we just talked about the solids. So we'll pick it up with the next chapter next week. We'll split it in half because of the Thanksgiving holiday. So and I'll actually delay next week's homework, the Thanksgiving week homework, into the next week as well, because I know it's a crazy week for the holidays and everything. Even with a pandemic on, I understand that there's still holiday obligations, and I don't want to get in the way of those, especially this year, right? But if there's anything I can do to help, let me know. I know I don't have anything in writing here. I know you're all missing my beautiful handwriting, and I apologize profusely for that. But I hope you understand as well how much I spared you watching me for like an hour try to draw these structures, right? I mean, come on, I'm not making that happen. Like, there's like shading and stuff. No way, not gonna work. But if you do have questions, let me know. I'm happy to help, and I totally understand if there's something that slips through the cracks in this video where maybe it would have helped to have some writing. I totally understand. But just, go back through it, pull, what I say in your notes as best you can. and yeah, enjoy the next level here. All right, we're talking about multiple particles interacting with each other, and not reacting, just hanging out together. Okay, and so we'll build on that more in the coming weeks, where it won't be pure substances. We're going to take these ideas and bring them to mixtures. So before you know it, believe it or not, these will be the good old days. All right, enjoy.